Hello and welcome to Algebra 2, Chapter 8.6. One of the more important sections in Chapter 8, we're now going to be solving exponential and logarithmic equations, which really means we are going to have to put together everything that we know about exponential functions and logarithmic functions. And before we start, I do want to return your attention to 8.4, and you might want to have these handy. When we wrote down let log base b of b to the x was x, and that b to the log base b of x was x, because those are going to turn out to be handy as we go through this section. So item number 1 on our list is that we want to solve exponential equations. So exponential just meaning we're talking exponents. And so if you have the same base to different exponents and they're set equal to each other, those exponents have to be equal to each other. So if you had 2 cubed equals 2 to the x, what does x have to equal? It has to equal 3. There's nothing else that you can take 2 to the power of that would still equal 8 in that case. So if we look at 2 to the 4x equals 32 to the x minus 1, I did say that they have to have the same base. So can you write these so that they have the same base? If this is 2 to the 4x, can you write 32 with 2 as a base? 32 equals 2 to the 5th. So this is 2 to the 5th, essentially then to the x minus 1. What do you do when you have an exponent to an exponent? You multiply, and so that gives us 2 to the 5x minus 5, because you're going to distribute there. So if they're both a base of 2, their exponents have to be equal to each other. So you set 4x equal to 5x minus 5, and then solve. So we're going to get negative x equals negative 5, divided by negative 1, x equals 5. Alright, so the key thing to doing this property is that the bases do have to be equal to each other. So if we already have a base of 9, then what we're going to want to do is make the other one have a base of 9. So 2 squared to the 3x minus 2. And then realizing that we multiply exponents to exponents. This is 9 to the 6x minus 4, which means that 2x equals 6x minus 4. And then if we solve from here, oh, I moved them to the same side, that's okay, plus 4, so we get 4x equals 4, x equals 1. So the next thing we're going to look at is what happens when you can't make them have the same base, because it's pretty convenient when you can, but what happens when you can't? And so to do this, we are actually going to take the logarithm of each side. Just like if you were to square each side, we're going to take the logarithm of each side. So we have 4 to the x equals 15, and there's no way for us to write 15 as a 4 to some power. So we're going to come in here and we're going to do the log of each side. So kind of maybe make it so you can read it. So the question becomes, what base do I take it to? Alright, so what do you think? I'm thinking base 4. That's a 4. Because if we have log base 4 of 4 to the x, based on what I had you write down at the very beginning of the section, what is that? That is just x. And so the other side then is log base 4 of 15. And if we use our change of base, that's log 15 over log 4, using a base 10 there. So then we are going to need to use our calculators. Log 15 divided by log 4. And we go to 3 decimals, 1.953. Alright, so let's look at another one of those. there's no way for me to write 18 as 5 to some power. And so I want to take the log of each side. And so what base do I want to use? I want to use 5. So I'm going to do log base 5 of the left and log base 5 of the right. Okay, because log base 5 of 5 to the x is just x, which is going to equal log base 5 of 18. Using your change of base, that's log 18 over log 5. Dividing that on our calculators, we get 1.796. Alright, so just a little bit different here. You really want to get just the one exponential term by itself. And so we are going to want to subtract 3 first. You can take the log of a sum, okay, if I wanted to, because you're taking the log of the side, so you would be taking the log of this whole sum, which you would then have to condense that. And it's probably better if you just go ahead and get the exponential term by itself, save you a little bit of headache. So 5 to the x plus 2 equals 22. And then I want to do log base 5 on each side. So in this case, you do get x plus 2 equals log base 5 of 22. And so to go ahead and compute that, log of 22 divided by log of 5, that side becomes 1.921, and then we'll subtract the 2 from both sides, and we get negative 0.079. So much easier if you go ahead and get your one term by itself. Alright, so the next thing we're going to look at are logarithmic functions. We just looked at exponential ones. So same deal though, if they're both log base b and they're equal to each other, then it turns out x has to be equal to y. Alright, so log base 2 of 2x minus 1 equals log base 2 of x plus 5. So if they're both log base 2, then what you have here, they have to be equal to each other. So very nicely, we're just going to set those equal to each other and solve for x. And I get that x equals 6. Alright, so just to move on here, so what happens when it's not convenient to write them with the same base? Or what happens when they're not both log base b? Okay, so what we're going to do here is called exponentiating the sides. Okay, that means we take the side as the exponent, so we're going to add a base to each side. So let's just say that x equals y, and so to exponentiate you're going to add a base, so we could say b to the x equals b to the y. Alright, so to show you what exponentiating looks like, so first of all, this is going to go off the property we referred back to at the beginning, the b to the log base b of x equals x. So as long as this base and this base are the same. So one way you could solve this is by exponentiating, and you're going to make both bases be 4. And you want the bases to be 4 because then that matches that right there. So 4 to the log base 4 of x plus 3, this side, just then gives you x plus 3, and that's going to equal 16 because that was 4 squared minus 3, x equals 13. Okay. Now there are times that you could actually do this without exponentiating, and so this is one of those times. You could refer back to 8.3 and change this from being in logarithmic form to exponential form. So remember then that we would have 4 to the second power equals x plus 3 and that would give you the same equation. But depends on where your variables are. There are times you are going to have to exponentiate, so we're going to practice that. Alright, so again, I want to exponentiate both sides, and so I'm going to, what I have here is going to become my exponent. I'm going to do a base of 5 on each side, because 5 to the log base 5 of x minus 4 just becomes x minus 4 equals 25. We're going to add 4. We get x equals 29. Alright, so just like with square roots and fractions, we are going to need to occasionally check for extraneous solutions. So these are solutions you get that don't work. So because the domain is generally not all real numbers, we should always check for extraneous solutions, meaning because not every real number is going to work, you need to check for extraneous solutions. Here you're going to find that your extraneous solutions are something that gives you a negative in the log. So like log base b of, let's do -2 equals x. If b has to be positive, there's no power you're going to raise it to that's going to give you a negative right there. So that number, where that -2 is, has to be positive. And so that's one of the things we're definitely going to look for when we check for extraneous solutions. Okay, so we got log base 2 of x plus log base 2 of x minus 7 equals 3. My suggestion on this is going to be to condense the left-hand side first. So using those properties from 8.5. So if I'm adding, then I'm going to be multiplying. So I'm going to have log base 2 of x times x minus 7, which I'm going to switch into log base 2 of x squared minus 7x. And that's going to equal 3. And so this would be a time that I would exponentiate both sides. We're going to do to the power, or 2 as a base. And so that's going to give us x squared minus 7x equals 8. And this time we happen to have a quadratic. And this can happen at any time. But then we need to remember that to solve a quadratic, we probably want to set it equal to 0. So subtract 8 over. And you're going to want to probably start by seeing if it factors. If it doesn't factor, you're going to have to use a quadratic formula. Well, let's see here. X minus 8, x plus 1. So it looks like it factors, which leaves us with x equals positive 8 and negative 1 as our answers. So if we put them into this logarithm, log base 2 of 8, you can have that. But log base 2 of negative 1, you can't have that, okay? So the negative 1 is not going to work, okay? And in fact, in the other one, the negative 1 would have given you a log base 2 of negative 8, which definitely wouldn't have worked either. So we just have the one answer. Alright, we're going to look at one more example here. So once again, we're going to go ahead and condense because we have this sum. And they're both log base 6, so log base 6 of x plus 5 times x, which is going to be log base 6 of x squared plus 5x. By the way, extraneous solutions don't just always happen when you have x squareds in there. Alright, so we're going to exponentiate both sides, so 6 to that side is going to leave us with x squared plus 5x equals 36. And we want to set it equal to 0. Alright, and we are going to factor this. So I think we get x plus 9, x minus 4, which gives us x equals negative 9 and positive 4. And if we look right here, which one of those will not work? The negative 9 will not work. And just to make sure in the other one that 4 works, yep, so x equals 4 is our only answer there. Alright, there is 8-6. We'll do some of those word problems we skipped over in class. Let me know if you have any questions, and have a great day.